Good evening, everyone. As part of my mini assignment under CE 611 Computer Vision course, this presentation addresses a real-world problem, spam detection in images using computer vision techniques. To ensure a deep exploration of the topic, our group divided this case study into 6 focused subtopics, each presented by a different member, as shown here. Myself, Anup Mandal, I'll be showing the case study number 1, hybrid feature extraction. This case study is based on the research paper titled Hybrid Feature by Combining Visual and Text Information to Improve Spam Filtering Performances. The problem tackled in this paper is that image spam is significantly more difficult to analyze than text spam due to its multimodal nature. Traditional text-based spam filters often fail when spam content is embedded in images using fonts or deceptive formatting. To overcome this, the author proposes a hybrid approach combining both visual and textual features for improving classification performance. The proposed method consists of 3 submodels: text extraction via OCR, topic and word embedded extraction using LDA and word to vec, and third one, visual feature extraction using CNN. These extracted features are then combined to generate a rich image representation which supports better spam classification. Continuing with the architecture, the paper outlines how these submodels outputs are fused for classification. The topic-based word embedding and convolution-based features are merged into a single one-dimensional vector. This is fed into a fully connected neural classifier, which outputs whether the image is spam or ham. This fusion approach was chosen because each model brings a unique advantage. OCR captures embedded text, NLP captures semantics, and CNN captures layout and visual patterns. In summary, this case study effectively demonstrated how hybrid feature extraction can improve the reliability of spam detection system. It also shows a multiple computer vision and machine learning technique can be integrated to solve complex real-world problem. Thank you so much. Now I will be handing over to Biswadarshi Naik. You can start.
Okay. So, myself, Biswadarshi Naik, registration number 242602. I have tried to practically show the CNN-based spam classification. So, our CNN model is designed to classify images as their spam or not spam. Unlike traditional methods like SBM or KNN or CNNs automatically learn and extract important visual features directly from raw images. This makes them highly effective even against challenges like noisy background or distorted text. The model consists of convolution layers for feature extraction, pooling layers for dimensionality reduction, and fully connected layers for final classification. Overall, CNNs offer better accuracy and generalization for image-based spam detection. Next. Uh, okay. We use OpenCV for pre-processing to ensure consistent and clean inputs. The cv2.resize that standardizes image sizes. cv2.canny, it highlights important edges like text and shapes. And cv2.cvt color simplifies the data by converting images to grayscale. For training, we use binary cross entropy as the loss function and Adam optimizer for fast and effective learning. The model is trained over multiple epochs with dropout layers to prevent overfitting. As a result, we achieve high accuracy, often above 99%, with very low false positive rates. Okay, next slide, please. Next. So this is the dataset I have taken from Kaggle. you can see this contains 1731 images, and spam and non-spam images are more or less similar in percentage. The training and testing dataset size is splitted in 80 to 20%. Next. I have taken two convolutional layers and two mixed pool layers with 3x3 kernel size. Then I have taken 128 neuron dense layer and dropout in between. That's it's a 0.5% dropout layer. So with this, I can achieve around 96% of accuracy. Next slide. You can check the predictions. These are 15 images, and almost all images are predicted in true levels. Next. Thank you.
Thank you, Naik sir. Now I'm Lieutenant Colonel Anshul, 242603. I'll be taking over from here and I'll talk about the next subpart of this particular case study, that is near duplicate detection. The objective of this particular case study is to detect the images that are nearly identical, however, but they are not exactly the same. This is a common requirement for various things like copyright detection, content moderation, and digital asset management. There are two approaches which are used here. The first one being SIFT, that is scale invariant feature transform, and the second one is histogram matching. In SIFT, it detects the key point in the images that are invariant to scale, rotation, and illumination. It is useful for matching features between slightly altered images, that is, if some image has been resized or cropped, or slight color shift in the version. In histogram matching, it compares the color stroke intensity distribution between the images to check for similarity to the visual content. The two techniques which are used here are perceptual hashing as well as wavelet-based similarity analysis. In perceptual hashing, it creates a compact representation or a hashed representation of an image based on its appearance. And very small differences in the image can lead to small changes in the hash table. That is, they are robust to minor edits like compression or scaling. In wavelet based, this analyzes image frequency component using wavelet transform. It is efficient at capturing both coarse as well as fine level detail across the scales. It helps differentiate images based on structure and content pattern. The key features being GMM, and Jensen-Shannon divergence. GMM, which is also known as the Gaussian mixture model, it is used to identify templates or clusters of near duplicate image structure. It helps in classifying and grouping similar looking images in a dataset. However, the Jensen-Shannon divergence, a symmetric matrix, is used to measure similarity between two probability distributions. It is useful for quantifying how close the two images are, and it is based on their visual content and encoding. Surprising to see a result of 6% improvement over the traditional detection method. The baseline likely include raw pixel comparison, basic histogram matching, or naive hashing. The improvement demonstrate the effectiveness of multi-technique hybrid approach. In the visuals, the grid shows is the slide highlighted the near duplicate image pair. Its matched key point are drawn to visually improve the effectiveness of the detection mechanism. At the last, this case study showcased a multi-layered approach using classical computer vision, statistically similarly measures, and clustering to enhance the accuracy of near duplicate image detection, especially in challenging scenarios where basic techniques fail. Thank you.
I'm Lieutenant Commander Rishabh Sagar, registration number 242604. We'll be dealing with the case study number 4, that is social media spam hunter. We all know that social media can be a boon in the right hands and a bane in the wrong, as seen in the recent Indo-Pak war. Spammers can significantly harm the user experience and even pose security threats. In this case study, image-based spam detection using CV2 was done. CV2 is a Python wrapper for the OpenCV, which is nothing but open source computer vision library. Next slide, please. As we all know, there is a proliferation of spam images on social media. It can either be to forward some propaganda or for spreading nuisance. The text embedded in images bypasses the traditional filters. Unclear and edge-dense spam content is normally present in this kind of images. Next slide, please. Here, CV2 plus a deep learning approach was used. We can use canny edge technique for edge detection and pre-processing for OCR. Multi-channel CNN was used, in which raw images and edge image channels were used, and platform-specific data augmentation was done. Next slide, please. Using techniques like canny edge detection to identify the density and distribution of edges, spam images might have more cluttered or irregular edges, which are caught by the edge detection techniques. These edge patterns highlight spammy layouts. The OCR extracts the embedded text. TF and IDF weighing is used for textual relevance. Next slide, please. Profile pictures are basically checked by checking the pattern and doing the pixel level analysis. The embedded spam URLs in bios and posts are also checked by similar words. Next slide, please. Here, the accuracy was found to be 96% on spam hunter dataset. The precision and recall high detection with low false positive was found. The key takeaway from this case study is multimodal inputs will improve the detection. Thank you.
Good evening, I'm Lieutenant Commander Suraj Menon. I'll be covering the case study 5, which is actually a fusion version of traditional and deep learning techniques for image spam detection. In the traditional methods, the OCR is used to extract the embedded text in the image, with using the conventional methods using like color histograms, edges, and LBB features. And the deep learning technique uses ResNet or VGG for visual feature extraction. And the fusion strategy is nothing but combining both these methods to primarily to merge it into a single vector and classify using techniques like SVM, random forest, or FCNN. So next slide. So the approach, in the first approach, the text features are segregated using OCR and linear discriminant analysis, and the visual features are explored in DNN in deep network using CNNs, and the classification is as told already using SVM and random forest. So the accuracy while using this as said in the source, which is the MTPI Electronics Journal, it was found that it was the accuracy was coming around 94.8%. And it was found to effectively handle the OCR evasive images. So that's it.
Thank you, Suraj. I am Yogesh Prabhu, registered number 242606. Till now, we have seen various techniques that have been in practice for the image-based spam detection. In this part of presentation, let us look into the difference between OCR and the deep learning approaches used in image-based spam detection. As you all are aware that the OCR is a traditional and straightforward method that analyzes an image, identifies individual characters, and then translates those characters into a digital text format. It is quite simple to understand and implement. On the other hand, deep learning methods, especially using the neural networks or the transformer-based vision models, treat the image as a whole and learn to classify spam or non-spam from raw pixels. Next slide, please. Now, let us see the core techniques that have been used in OCR and deep learning methods for the feature extraction in the next few slides. The first case is the OCR block diagram. In this slide, the block diagram shows the OCR-based spam detection. First, the text extracted from the OCR is converted into a token in the form of a word through tokenizer. Each token is converted into a integer corresponding to its word through the vocabulary and then transferred to the embedding bag. The embedding bag generates the outputs, generates and outputs embedding vectors of each word. This is what happening in the OCR based approach. Next slide, please. On the deep learning side, generally text-based spam filters do not perform well unless accurate text is provided. Therefore, in order to overcome the limitations of the text-based spam filters, information other than text must be able to utilize to the fullest. The spam image feature extractor described in this block diagram extracts various features of spam from images using the convolutional layers and the pooling layers within the CNN model and outputs them as vectors. The CNN for the spam image features, the previous slide please. Here the CNN for the spam image feature extractor consists of 4 convolutional layers and max pooling layers, and it uses the rectified linear unit, that is ReLU activation, as a function. And now we understand the core difference between the OCR and deep learning based approaches. Next slide, please. Coming to the direct comparison between the OCR and deep learning, when comparing the OCR based and the deep learning approaches for image based spam detection, each has its own strengths and trade-offs. OCR based methods like using Tesseract or ECOCR focuses on extracting text from images and then applying NLP, natural language processing algorithms, or traditional machine learning models to classify spam. This approach is lightweight, integrates well with existing text-based spam filters, and is effective when spam contains clear and readable text. However, it struggles with the distorted fonts or the background embedded text or the CAPTCHA kind of stylish tricks. On the other hand, deep learning methods, particularly CNNs, bypass text extraction and learn visual patterns directly from the raw images. They excel at identifying complex cue like fonts, textures, and layout distortions, offering higher accuracy on the noisy or stylish spam. While deep models require larger data sets and more computational resources, they are adaptable to evolving spam techniques through fine-tuning. OCR is faster and simpler to deploy in legacy systems, but deep learning, though heavier, provides a more robust and scalable long-term solution for the modern spam detection challenges. Next slide, please. Starting again with a comparative analysis. In short, OCR is faster and simple, but struggles with visual complexity, whereas deep learning is more powerful and adaptive, but comes with a greater resource demands. As an ideal solution, we can combine both, use OCR to extract explicit text features and use the deep learning to understand the image as a holistic. As image spam continues to evolve, hybrid models are increasingly the future of the robust detection. The next slide, challenges and solution. Image spam is often crafted to avoid the traditional text detection techniques. So when we are using the OpenCV, in short CV2, and computer vision for image spam detection, several practical challenges arise. One is the lighting variation and compression artifacts, obfuscated text. In lighting variation, spam images may come from a screenshot or some photographs with inconsistent lighting. So that will lead to uneven illumination, causes poor contrast, and reduces OCR accuracy. The second one, compression. Spam images are often compressed to reduce the size, which introduces the noise and blurring. So that is another drawback. So artifacts, obscure edges, and text clarity affecting both OCR and deep learning feature. And obfuscated or stylish, we can say that stylish text. Spam creators often use that distorted or rotated fonts or cluttered backgrounds. So because of this, the OCR fails to extract text and conventional feature detectors get confused. These are all the challenges we got. And the emerging solutions are with a GAN-based detection. That is, the generative adversarial network can simulate spam and non-spam image patterns Then vision transformers. Unlike CNN, vision transformers analyze the image as a sequence of patches and use attention mechanism to capture long-range dependencies. At last, the real-time hybrid pipelines, it uses the combination of both OCR and the deep learning. So we extract the text using OCR and analyze those text and the visual patterns using the CNN or the vision transformers. Next slide, please. So as a summary, we have listed some of the OpenCV functions that can be used for image-based spam detection. The overall workflow typically involves the standardizing of image dimensions, extracting relevant features like edges or textures, applying augmentations like rotation or noise to train robust models, and finally using OCR pre-processing to support text-based analysis. These techniques collectively enhance the system's ability to detect spam embedded within the complex or deceptive visual content. Next slide. Before I conclude, I would like to acknowledge the key references that are used in this case study. For anyone interested in deeper insights or implementation details, I highly recommend checking out these papers which are available online. Thank you.